What I'm going to do today is some stuff on practical physics, okay? And so this is a Vernier caliper. And this is a Vernier scale. And I'm just going to briefly remind you how to use a Vernier scale. So the very first number that you have to get is it's how many in millimeters. Can you see these are in centimeters? That's 0, 1, 2. These are centimeters, right? And can you see it's 2.7 there? So the 0 on this scale is a bit bigger than 2.7. So the answer is 2.7 centimeters, right? And then what we've got to do is we've got to get the next significant figure, okay? So this is centimeters. We want the next significant figure, okay? And how do we do that? Can you tell me how we do that from the scale? So what we're doing is we are looking for the lines at the bottom which line up with the ones at the top, okay? So you just move along and move along and move along and move along. And can you see that one there, that one's slightly to the right of the line above it. And this one there is slightly to the left of the line above it. And that one is perfectly aligned with the one above it, which means that the next two significant figures are 7, 5. So this is in centimeters. Okay, now this one can go to 4 significant figures, this particular one. Okay, right now I'm going to clear all of that and I want you to have a go at these Vernier scales. So I think perhaps I'll make it a bit bigger. Okay. So look at the scale and figure out what the reading is. And when you've figured out the reading for A, I want you to pop it in the chat. It's not so many significant figures on this one. Okay, do I need to do the first one with you? So can you see this is centimeters? So this is 0 and this is 1 centimeter. So can you see this is 0.1, 0.2. Can you see it's not as much as 0.3 where that 0 is? So it's 0.2. And then what we're looking for is the line here that's lined up with the one above it so that we can get the second significant figure in this case, second one. Okay, so, and I think that that one is slightly to the right and that one is slightly to the left. So I think it's that one. So it's 0.28 centimeters, this first one. Can you work out the second one? It's actually there. That's why that's what we're reading. Come on, guys, pop it in the chat, please. It's not as big as a centimeter, so it's 0 point something. This is 1 millimeter, this is 2, this is 3, this is 4, this is 5, and it's not as big as 6. So it's 0.5 something. Which one of these lines along the bottom scale is lined up with one of the ones on the top scale? I think it's that one, which is 7, which means it's 0.57. Well done, Annika. Okay? Or Anika. Oh, I don't know how to say your name. Okay. Right. Next one. Can you do the next one? we're reading there. It's not as big as 1 centimeter, is it? So it's 0 point. Well, of all of these lines at the bottom, the one that I think is lined up is that one. So I think this is 0.90. Can you do this one? You're reading that point there. Well, it's certainly not as big as 1, so it's 0 point something. Come on, guys. Well done. 0.07. It's not as big as 0.1, so it's 0.0. And then the one that's lined up underneath, I think is that one. So it's 0.07. Well done, Annika. Right, let's clear all of those. We're on E now. Let's just do 3 more. Now this one, it's bigger than a centimetre. There's the centimetre mark. It's not quite as big as 2. Can you see it's kind of in there? So it's 1 point something. Can you see that that's 9, 1.9 to get to there? It's bigger than 1.9, but it's less than 2. So 1.9 something. What's the next significant figure? I don't think that that one's lined up, which would make it 1.97. Yeah, either 1.98 or 1.99. Yeah, I would have gone 1.98, but 1.99 would be good too, or maybe 1.99. Okay, I think that that's about right. Okay, right now let's do the next one. What's this one? Come on, guys, somebody other than Annika. It's bigger than 1, less than 2, bigger than 1.5. What's the next significant figure? Yeah, I think 1.53. Well done, Valmic. Okay, I think we've done enough of those. Okay, that is a bit of practical practice using a Vernier scale. Right, the next one is a micrometer. Right now, before we do the quiz, I want you to practice measuring. So here we've got a practice example. This is from Isaac Physics. Right now, if I go to the micrometer here, you can see that we've got a, a column, a cylinder here, which has got graduations on. Okay, and these ones are millimeters. Okay, not centimeters, millimeters. And you can see that you can get quarter, half, three quarters, one, quarter, half, three quarters, two. Actually, I think this, yeah, no, I don't know. Anyway, what you've got to do is recognize that every time this thimble goes all the way round once, it's not a whole millimeter that's been increased. It's only half of one. So what you've got to do is to work out how many half millimeters you've got, and then you've got to add on the fraction of another half millimeter. Okay, I know it's a little bit complicated. So we're going to have a bit of a practice. Okay, so let's go to here. Okay, we are measuring that point there. Okay. So can you see we've got naught, we've got one. I think these might. I don't know if these are in inches. I don't like this. I don't like this. I've changed my mind about this this one. Not going to do that. I want it to be clearly in centimeters. So let's go back to the Isaac physics one, wherever that was. Where was it? Where was the Isaac physics one? Yeah, can you see it's in inches? We don't want it in inches. Let's go metric. All right, I think these are in millimeters. Yeah. Okay, so let's use this one and you can see what I mean. Okay, so this is 0 millimeters. This is 1. This is 2. This is 3. This is 4. And this is 5. And can you see on the bottom we've got half a millimeter and a half millimeter and a half millimeter. So can you see that this is 10 millimeters, this is 11 millimeters, and can you see that I can also see 11 and a half millimeters, which is why this first number is 11.5. And then this spindle, this thimble it's called, which is rotates, one complete revolution is half a millimeter. So can you see we've got to add in the fraction of a complete revolution, and the complete revolution will be 0 to 50, representing 0 to half a millimeter. So can you see we've got 22 there. So it's 11.5 plus another 0.22, which gives you the reading of 11.72. Okay, so now let's have a little look at this one, just to give you another bit of a practice. Okay, so we've got 5 millimeters plus another half millimeter. So we've got 5.5, and then we've got to add this fraction of another half. Can you see it's 35, 36, 37, which is 0.37. So we end up with a 7. The 5 and the 3 is 8.5. So we end up with 5.87 millimeters from that reading. Okay? I hope you can figure this out. Right. So now I want some examples. That's what I want. Are these metric? These ones are metric. Can I get to them? Oh, Okay, so these are in millimeters. And I'm just going to make it a bit bigger. Okay, so I don't want to see the answer. Can I do that? Yeah, no, I don't want to do that. I want to see the questions. So let's just do these first two. These are in millimeters, people. Millimeters. Let's have a go at this first one. What does this one read? So that's 10 millimeters. That's 11. That's 12. That's 12 and a half. So we've got 12.5. And then we want the fraction of a half. Can you see? We've got 15, 16, 17, 18, 19. So it's 12.69. Can you see? Now do this one. What do you get? Do number two. Okay, so this is 20, 21, 22, 23.5, 23.5. And then this, it's nearly all the way around. It's another 0.49. So it becomes 23.99 millimeters. Well done, Annika. Okay, let's try one more. I hope you're getting this. What's this one read? Okay. One. So this is naught. This is one. This is 1.5. 1.5. And then the fraction of another half millimeter is 39, I think. We have to add them. 9, 8, 1.89 millimeters. Well done. Okay, final one. This is the last one. Don't let everybody else just do it for you. Do it yourself. It's the only way you can be sure you're getting them right. Yes, it's exactly 5.50 millimeters. Okay, because you can see it's not 5, and you can't see the halfway line, but it's sitting on the 0, so it must be exactly halfway between 5 and 6 millimeters. Okay, good. Notice that you must put that 0 in because it's a number that you can actually tell what it is. Okay. Incidentally, what's the uncertainty on that reading? What is the absolute uncertainty on this reading? This one. Plus or minus. Okay, what is, yes, plus or minus 0.01 millimeters. Yes, because it's the smallest change that the instrument can measure. Okay, it's called the resolution of the instrument. So it's the smallest thing that the instrument can measure that will make a difference to the measurement, and that's the absolute uncertainty. If you've got just one reading, if you've got multiple readings, it's slightly different. Okay, so let me pull up. I want let's just do a ruler. That's not going to work. Right, I want a nice close-up picture of a ruler. Okay, this is a 30 centimeter ruler. 30 centimeter ruler. What is the absolute uncertainty, please? For measuring the, I don't know, the length of a page or something with a 30 centimeter ruler. Yep. It's plus or minus 1 millimeter, because 1 millimeter is the smallest thing that you can measure with this instrument. Okay. It's technically it's 0.5 millimeter at one end and 0.5 millimeter at the other end, but it's basically it's 1 millimeter. Okay. So that is the uncertainty for a 30 centimeter ruler. What about a regular classroom protractor? Right. What is the uncertainty on this protractor? Yep, plus or minus 1 degree. 1 degree. Perfect. Okay. Technically half at one end, half at the other. Right. Brilliant. We're doing good. Right. Let's see if we can find, I don't know if they sell the multimeter. Oh, I want one with a number on it. Show one with it actually moving, but measuring something. Hmm. Okay. You can't see what that's saying, but it's actually it's measuring. Ooh, that's weird. Right, can you see on this picture? It's measuring volts and it's AC. Okay. That's what this picture is showing. What is the uncertainty on this instrument on that scale? It's measuring volts. Yes, it's 0.1 volt. It's 0.1 volt because that is the smallest change that you can measure, that you can see on the, makes a difference to the reading, right? It's the smallest change. So it's 0.1 volt. So it's this number, the least significant one, changing by 1. Okay, that's what you could read with that one. Right, let's go for a classroom thermometer. Accurate. Oh, let's take out the word classroom. Oh, okay. Well, let's go for a digital one then. This one. What is the uncertainty in the reading? Come on, guys. What's the uncertainty in my temperature reading? What's the smallest change that it would be able to read? Yes, 0.1 degree. Okay, because if this number changes by 1, you'd be able to tell. Right, with digital instruments, the next significant figure, it's not rounded. It's literally cut off. So this next number might be a 9 or it might be a 0. You just don't know. And they literally just cut it off. You don't know what the next. So you can't do half measures on a digital instrument. Can't do it. Okay. So it is right now. Now, this is where things get confusing. If you have more than one reading of something, imagine that you've measured the current in a circuit, and you've measured it once, and then you went away because somebody called you, and then you came back, and oh, it's reading something slightly different, and you watch it, and it changes again, and you watch it, and it changes again, and you write down, I don't know, 5 or 6 different readings for the current. Okay. In that circumstance, what would your current reading be? And what would your uncertainty be? Right, so I'm going to imagine that we've got a current of 3.5, 3.6, 3.5, 3.4, 3.5, 3.5, 3.4 amps. Okay, so they're all readings of current, okay, from the same circuit. So they're all just as valid as one another. What would be your reading? And what would be your absolute uncertainty for the current? Okay, you don't actually have to do it. Tell me, how do you get the reading? What would you do? Take an average. What sort of average? Mean, mode, median? Mean. Okay. So I would add them all together and divide by however many there are. So there's 1, 2, 3, 4, 5, 6. There are 7 readings. So I'm going to do 3.5. How many of those are there? 1, 2, 3, 4. Okay. Plus I've got a 3.6 and I've got 2 3.4s. And I'm going to divide by 7, and I get 3.4857. Okay, and it keeps going, right? So that's my current and my uncertainty. How do I get my uncertainty when I've got a range of readings like this? Because it's more than the 0.1. Yes, okay. So the absolute uncertainty is the mathematical meaning of half the range. And half the range, it's half of the maximum value minus the minimum value, right? Which is half of 3.6 minus 3.4, which is actually 0.2, isn't it? Half of 0.2 is 0.1. Oh, it works out to be the same, okay, as it would be for just one reading. So we can say that I is equal to 0.1. This is in amps. Right, what's this number? Do I write all of that or not? Yeah, you would round it to the point something, right? Because it's plus or minus 0.1. So we would write 3.5. Okay, that is the current. Right now, what if this one wasn't 3.4, but you'd got 3.9? What would you do with that 3.9? Would you include it? Why would you exclude it, Helena? I'd hesitate to say it's an anomaly, but it is definitely an outlier. Okay, so if you'd got one that was 4.7, that would be an anomaly. There's chance there that somebody's just read it wrong. Okay, that's an anomaly. But there is something to be said for excluding the maximum minimums. And if you've got one that's miles away from all the others, that means that it's probably not a reliable reading and you should exclude it. You should exclude it from your range. You should exclude it from your averaging process as well. So you would just not include it. Not include it. Okay. An outlier is something that's just on the edge of the range. An anomaly is one that doesn't fit the pattern. Okay, so let me do this. Right, the easiest way to see a pattern is to plot the points on a graph. So let's imagine, right? And what we're going to do is we're going to draw a straight line, okay, of best fit through this 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 set of numbers, this set of readings. So, right, okay. I'm going to add one more reading. Right now, I would call that one an outlier, and I'd call that one an anomaly. But you could reasonably call them both anomalies. Can you see this one really doesn't fit the pattern? The chances are that somebody transposed numbers or somebody pushed a little car down the ramp or whatever it is you're measuring, right? Okay, that's the difference. Right. Okay. Let's ooh, didn't mean to do that. Diagram as code. Goodness me. Right, okay, so now we've got lines of best fit. Okay. What do we do with our error bars? What is the use of error bars? Right, so I'm not going to include this one. And I'm not going to include this one. But I'm going to put my error bars on here. So what's the point of error bars? What can you do with them? Now I've got, imagine I want the gradient. Okay. What do? I measure my delta y and my delta x, don't I? So this distance is delta y, and this distance is delta x, and my gradient is equal to delta y over delta x. Right. Now, this is y, this is x. Right. So now, if I wanted to know my uncertainty in my gradient, I could do what Helena has just said. The steepest and the shallowest lines that still go through all the error bars. Okay, so I'm going to change my pen for a different color, and I'm going to draw the steepest line I can that still goes through all the error bars. Right. Right, I think that's about it. Can you see that if I make it any steeper, it won't go through that one, and it won't go through that one. So I can't go any steeper than that purple line. Or is it blue? I don't know. Blue? Anyway. So that is my steepest line. So that is what's called the line of worst fit. So now, if I measure the gradient of my line of worst fit, delta y over delta x, I can then take the difference between those two gradients, and that is my absolute uncertainty in the gradient. So it's the difference, it's the absolute uncertainty. So I would go, so my final answer for the gradient, which I'm going to call big G. So it's big G, that's my best guess, that's my line of best fit. Okay, that's my line of best fit gradient. And my uncertainty is the purple G minus, oh, I want it in black, minus the black one. So that's my steepest line of best fit. That's my best line of best fit gradients. That's my uncertainty in my gradient. So to get it as a fraction, so that's my absolute uncertainty. Let's write that down. Absolute uncertainty in the gradient. Okay, so can you see that if I wanted to quote my gradient when I've got a line of best and worst fit, I would write that my gradient is equal to, right, it's big G plus or minus, and then it's going to be purple G minus black G. That's my uncertainty. Okay, and then you'd have to put the unit in here. I don't know what it is. Unit, I'm just going to write unit. Okay, so it's plus or minus. This is my absolute uncertainty. Okay, right, how would I, right, let's do, R is equal to 0.5 5, 0, plus or minus 0.01 centimeters, right? And I'm going to ask you to tell me what is the uncertainty in the area. This is the radius of a circle. What's the uncertainty in the area? So the formula for area is pi r squared. So how do I work out my uncertainty in my area? What do I do? Radius times 2. That's not my uncertainty. What do you mean by radius times 2, Verdant? You're not being specific enough. Right, first of all, these numbers are either multiplied or divided. So in order to work out my uncertainty in A, I have to work out my percentage uncertainties. So I can write down that my percentage uncertainty in A is equal to my percentage uncertainty in pi plus, can you see I've got R and then I'm multiplying it by another R. So it's the percentage uncertainty in R plus the percentage uncertainty in R again. So can you see it's my percentage uncertainty in pi plus 2 lots of the percentage uncertainty in R because R is squared. Right, so first of all, what is my percentage uncertainty in R? How do I work it out? From my absolute uncertainty, how do I work out my percentage uncertainty? So it is, you're right, Verdant. Okay. So it's my percentage uncertainty is my absolute uncertainty, 0.01, divided by the value, 0.5, times by 100. Okay, so we've got 0.01 divided by 0.5 times 100 gives me an uncertainty of 2%. Okay, so I want my area now. How do I calculate my area? Well, it's pi r squared. So it's pi times 0.5 squared, which is 0.785. I'm going to keep going, 398 centimeters squared. Okay, so that's my actual value for my area. Now what I've got to do is I've got to work out my percentage uncertainty in my area. So my percentage uncertainty in my area is equal to, right, well, it's a percentage uncertainty in pi. What's the percentage uncertainty in pi? 0, good, because it's just a number. Any number like pi or e or 2 or 9 or 7, any number doesn't have an uncertainty associated with it, not just a plain number. If it's a number that represents a variable, then it does. But pi doesn't have an uncertainty. So I've got 0 for this one, plus 2 lots of this 2%. So my percentage uncertainty in A is equal to 4%. But I don't want the percentage uncertainty. I want the absolute uncertainty. I had to find the uncertainty in the area, not the percentage uncertainty in the area. So How do I go backwards from my percentage uncertainty to my absolute uncertainty? So I need 4% of that. That's how I do it. So it's 0.78538 times 0.044%. So I get 0.031459, etc. Right? Or one. Right, okay. That is now my absolute uncertainty in A. So I can quote A. It is this number. Okay. How many significant figures do I use? I'm going to write them all to begin with. 78539 plus or minus 0.03141 centimeters squared. Okay. I've got too many significant figures. How many should I use? Can you see that that place value, that is where my uncertainty is? It's in the hundredths column. So I can quote to hundredths here. Yeah. So my area should be written 0.7 rounds up 9 plus or minus 0.03 centimeters squared. So everybody understand why? Okay. Do I need to go through anything here? If it wasn't the area that I was interested in, but imagine I had measured the lengths of two pieces of paper. So this one is L, and this one is D, right? And I want the total of L plus D. Right, now imagine the L was, I don't know, 12.1 centimeters, and imagine D was 8.9 centimeters. And that's all you've got. Nobody's giving you any uncertainties. I want, first of all, the total length. Okay, so it's 12.1 plus 8.9. So we do that and we get 21.0 centimeters, right? Now what I want is the absolute uncertainty in the total length. Well, first of all, what's my absolute uncertainty in this reading? Zero point 0.1 centimeters. Okay, so this one is 0.1. What's my absolute uncertainty in this reading? 0.1. Okay, and what I need to do here is I've got to add, because I'm adding or subtracting, doesn't matter if you're subtracting, but the absolute uncertainty is the uncertainty, absolute uncertainties all added together, okay? So it's 0.2. So if I'm going to quote my total length, including the uncertainty, I would write 21.0 plus or minus 0.2 centimeters. Okay? So the rules are these. If you are multiplying or dividing, then you add the percentage uncertainties. If you are adding, oh, I can't spell now. Or subtracting, then you need to add, and it's always add, even if you're subtracting, the absolute uncertainties. And if you've got powers, well, if you've got something squared, then you double, because they're multiplied, the percentage uncertainty for R. Okay. If you've got, let's imagine you've got A to the third, this is the mass number. Anyway, it doesn't matter. A to the third, what do you do with it? Here, it's 1/3 of the percentage uncertainty in A. Okay, right. In T to the 4, there is an equation with T to the 4 in it on your data sheet. What do you do with it? It's 4 times the percentage uncertainty in T. Okay? If you've got the square root of, I don't know, G, square root is to the half, isn't it? So it would be half of the percentage uncertainty in G. Can you deal with powers? Okay, right now, you will not have to deal with other functions, cosine, sine, logs, none of that. That is it from that point of view. Right, I want to do one or two other things because this is about practicals and apparatus. Okay, so let me see if I can pull up some equipment and see if you can name it. Okay. Okay, so I'm going to pull up some equipment and I want you to see if you can name it. How can I get a picture of just the thing? Hmm. Okay. Tell me, what is this instrument? What's this instrument called?
Set square.
Yes, say it again louder.
Set square.
Well done. It's a set square because guess what it does? It sets things square. Okay. You need to use one to measure the round things. Okay. Or to put things vertical or to put things horizontal compared to verticals. Lots of people forget what this is called. Okay. Right. Oh, that actually has the name of it on it. Okay. Right. I want you to tell me. What's it called? Oh, close that a minute. I want you to tell me what this is, please. Well, why won't it come up? The okay, hopefully. Can you see that? Doesn't say it on it. What is it? What is this thing? Okay. Yes, well done. It's an oscilloscope. Okay. And what does an oscilloscope do? Measures fields. No, it doesn't. It doesn't measure fields. Doesn't measure fields, sorry. Wave activity. Doesn't really measure wave activity. I mean, it sort of does. Okay. This thing is a glorified voltmeter. So all it is just a voltmeter. But this voltmeter has this facility that you get volts on this scale, and this is time. So basically, it's a graph of voltage with time. And the reason why you think it's to do with waves is because quite often you have a voltage that changes with time. And the only advantage of an oscilloscope is that you can see what the voltage is doing if it's changing with time. And it's always a voltage. You can attach a microphone to it. Okay, so there is my microphone, right? And I'm plugging it in to channel 1, and I get a wave out. But that is because the microphone turns sound into an oscillating voltage, which is what the oscilloscope reads. And I can have a signal generator, can't I? Okay, and my signal generator can produce waves that look like this, and waves that look like this, and waves that look like this. And my signal generator can change the frequency and the amplitude. And if I change the frequency, I'll get waves that look like this. Okay, and if I change the amplitude, let's clear all my drawings, on that scale, I would get waves that look like this. So nothing like so big. Okay. So an oscilloscope is just a glorified voltmeter. This axis is the voltage and this axis is the time. Okay, that's all it is. Yes, it looks like they're waves, and they sort of are, but they're sort of not as well. Okay, right, now this was a very practical session. I hope you found it useful and helpful. My experience is that lots and lots of people struggle with uncertainty and practical physics. Before I go, I want, I know there are some year 13s here. When you're doing an oscillation of a pendulum, how do you mark your middle position It's got a name, that mark. Begins with an F. Can anybody tell me the name of the marker that you put in the middle position, the equilibrium position of your pendulum swinging
The
backwards and forwards?
fiducial mark.
Well done. It's a fiducial mark. Fiducial. Fiducial. Fiducial mark. And the point of it is to mark the middle, the equilibrium position. Does anybody know why we mark the middle position? Why would that be an advantage?
It's where we measure the time period, like
Yeah,
from
why do we measure from the middle? Because it goes up to one end and it stops and it turns around, it comes back and it stops and it turns around, it comes back and it stops and it turns around. So why, yeah, and we count how many times it passes.
it's the equilibrium position. So
Yeah,
that's
but
like
why do we put the marker there and not at one end or the other end?
that's maximum velocity.
Why? Yes, yes. Now, why is that an advantage? And the answer is because it's there for the shortest length of time. It's going fastest, so it's at the middle position for the shortest length of time. So we can mark when it's there much more exactly than when it's at one end. Because as it comes up to the one end, it slows down, slows down, slows down, slows down. Stops, turns around, turns around. So when exactly was it at the end? Can you see? You can't tell, but you can tell when it goes to the middle. It's like now. Can you see? It's really very definite when it's in the middle because that's where it's moving fastest. So we count every other time it goes to the middle because it's when it goes through in one direction only. That's one complete oscillation, remember? So it's from there all the way to there, all the way back to there, and back to the middle, going the same way. So a fiducial mark. Those in year 13, you're going to need to remember fiducial mark for your oscillations, please.